shaft. Some people use bar, some people use shaft. And I prefer shaft, okay, because sometimes bar means the material under tension. Anyhow, prismatic, that means the cross sections of the shaft is uniform, is the same from in the axial direction. So right now we're talking the system we are studying, for example, like the circular shaft from the bottom to way up, or we consider any arbitrary the cross sections, a shaft with any arbitrary cross sections. So basically, depends on which level you pick, the cross section will be the same. It's the same. Doesn't matter. Say if this is the x, y, and the axial direction is z. So basically, the cross section is remain the same throughout the z direction. So that is the case we studied. So that means for this case, if we have the shaft, like this case, no, we won't discuss this case in this chapter. Okay, so here we can find our discussion. Before we proceed, and usually we're going to talk about assign three important assumptions, and those assumptions will allow us to make derive the closed form solutions. And the first assumptions and is very strong, and basically the first assumptions saying each cross sections once under deformed is rotated a rigid body rotation about the center of axis. What I mean? So if we consider this circular shaft, for example, and in a single cross sections, for example, we take these cross sections, okay, on that cross sections, and once it's twisted, then the point on the cross section in the XY plane is considered just do the rigid body rotation. Rigid body rotation, that means is this. Again, using the circular shaft as one example, and these are z directions. So if we take this cross section here, and let me label the x and y to here. So here, let me pick, say, a point, and say this point is region O, and this is P. So let me label that here. So this is P, and this is region O. Rigid body rotation simply is this. This is a rigid stick, and then rotating, and by a small amount of the angle. So this is called the theta, and move to P from here. Okay, basically from here to here, this rotating the track, the path, follow a circular path. Okay, that's called the rigid body rotation, and which means during the torsions, the radial distance keep the same. Okay, so that is the first assumption. And the second assumption from here is that here we talk about a small deformation. So that means when we rotate twist the shaft, we assume everything is in elastic deformations. Okay, and so for the second one, that means is this. Let me make another plot. So again, using this shaft as one example here. This is the axial directions and z directions, and x directions and y directions. The second assumption saying that, for example, for this illustration, let me fix the bottom face. Okay, the bottom face is clamped on the ground. And then from here, let me initially, before the torsion applied, let me take before the torsion applied, in the undeformed geometry, let me make a mark. Say using a permanent marker, I plot a line, and that line basically on the outer surface, just like here. Okay? And then after torsions, for example, say if I apply the torsion twist the shaft in this way, then this line will remain a straight line on the surface. But because the bottom side is fixed, this point will fix, won't change. The top point, per the first assumption, do the rigid body rotation. So this point, for example, if this, for illustration, let me utilize a circular shaft for illustrations. If this is circular shaft, this point, under the first assumption to the rigid body rotation, this point will be moved along the arc to here. For example, let me exaggerate the displacement, okay? Then this point moves to here, then you simply link this point from here to here, and that this straight line represents the deformed mark on here. So this remains as a straight line. That's basically telling the second assumption. So that means the amount of rotation is a linear function of the z-axis, which means, for example, we talk about here, that has the z at the level z here. Okay. This amount, again, at the point, a point at the z level, at the level z here, going to move along the circular arc to here. This amount, proportional to this amount, is in linear proportion z to the length L. Be good? Okay. Which means, if you want to measure the angle here, let me call this is the angle, whatever the angle, let me, I don't have a appropriate symbol using in the lectures, but let me just using alpha. Alpha is constant. Alpha is constant. As long as we keep the value of the torsion, then corresponding deformation once reaching the static equilibrium, then alpha equals the angle of the twist, which is a constant. Okay. So basically, the second assumption is saying in proportion z to L that tell us the arc length at a different level. Okay. The third one is a very specific note. The third one only valid for circular cross sections. The third one simply saying if the shaft is circular, is a circular shaft, then there's no warping. The warping is this. Again, let me utilize this as one example. So say this is the cross sections here. Okay. After deformations, these cross sections, before and after the deformation, this cross section will remain as a plane. Warping is a distortion such that in a cross section they have z displacement. Okay, so something like, if this is a cross section, okay, and after distorted, then the warping, again, this is z direction. Warping is before twisted is plane, and after twisted, for non-circular shaft, it would have something like this. Have the displacement in the z direction. We call it warping. Okay. But for circular shaft, there's no warping. Every point, all the points remain as a plane there. So the third assumption is only valid for the circular shaft. Okay. We were gradually using, in particular, the first assumption, second assumption to help us derive the closed form solution for torsions and for different shapes of the cross section. And by example, I will exercise the solution process for circular shaft. for elliptic shaft, and then for rectangular shafts. And rectangular shafts, basically, we're going to solve for the plus equation in rectangular domain. But anyhow, okay. So, so now we come to consider our model here. And again, in our model, I use XY plane, and that is pretty much persistent, consistent throughout the lecture notes. XY is in this, and using Z to denote the axial directions. And the dimension, the length of the shaft is using L, or capital L, okay? And here we assume this L dimension is much larger than any other x, y dimensions. So that is the assumption there. And why we want to consider this? Because we simply want to make this assumption there, make that linear, okay? Because when the shaft is pretty large, pretty long, then the shaft is pretty compliant. Any material compliant is not easy to deform into plastic, okay? It's very hard to produce any plastic deformation in a very compliant material. Okay, so that is one I would say. Okay. And here I use XYZ to denote the coordinates, and UVW for the displacement component. Okay, again, what is the UVW and in terms of XYZ? So again, we consider this using two-dimensional for example here. So say, for example, here is OP, and that is the candidate mark and mate on deformed object. And if this object, say this is the certain oblique object, when this object is under different kind of loading, P1, P2, and say pressures, okay, and then we confine this object in the appropriate way, say, given the certain appropriate constraint, such that after this loading, everything will reach the static equilibrium. Under these situations, due to the reaction to loading, this point will displace to here P prime. Okay, so that means in this way the coordinate, say let me say this is x, y, this is x prime, y prime. Again, from previously we learned the displacement is defined as the difference between the after and before. So here, in terms of the two-dimensional scenario, that one simply is x prime minus x and y prime minus y. So that is the definition of the displacement. Okay. So here for UVW, then we consider it three-dimensional. Okay. And in particular, for W, that indicating is a displacement in the z direction. And displacement in the z direction refer to this plotting here. And for shaft, in this kind of configuration, any displacement in the axial directions, we call it warping. So this word, the warping, is a very particular terminology only applied to shaft. Okay. Again, the warping indicating is the axial displacement of material point happen in the axial direction. We call it warping. Okay, so keep that kind of thing in mind. And so the warping, probably we can utilize this figure to have a better view. Okay, so basically warping, you can see all the cross sections before deformation is a plane, but after deformation is curved in this direction. So this one we call the warpage exists in this model. Okay, so and so now we can begin to this will be marked as the first page of the solution process. Okay. The first one, is this. Again, here I reformulate each section basically conducting the rigid body rotations. Okay. The second assumption, I introduce a term called the rate of the twist. Okay. Rate of the twist basically is this. Let me utilize this as an example here. And for alpha, that is the angle of twist. Okay, the angle of twist basically is this. If we have the shaft, let me put into another viewpoint. So here comes the breaking line here. So here this side is fixed against the wall. And when this is on the torsion here, this is the axial directions. This point is located before deformations, and after the torsion being applied to this point, A moves to A prime. So we measure the angle from this end, from the end here, and this angle is defined as the alpha. Okay, alpha is called the angle of the twist. Okay, and for the value to here, this one, assuming this length, is called the L. So angle of the rate of the twist, beta, simply in here, our lecture note simply is alpha divided by L. So that means that's called the unit, the angle of the twist per unit length. That's it. Very simple. Very simple. The definitions. Okay. So simply, if you want to say, you can visualize the beta is simply the angle of the twist per unit of the shaft, unit length of the shaft. That's it. Okay. And the third one, let me leave it and until the later we go forward. Okay. So once we have everything ready, so right now, again, before I erase these portions, the first one we know we have the angle of the twist, and angle of the twist is such that, imagine we fix one end, then we measure the total deformation in terms of the angle from the other end. So alpha is one kind of the measurement to how much the material is deformed. Different materials, the shaft made by different material under the same loading, it has the different angle of the twist. If you remember from the fundamental year 331, the angle of the twist equal to T L over GJ. Okay. From fundamental, the T is the given torque, and L is the length of the shaft. G is the rigidity of the modulus, and J is we call the polar moment of inertia. For solid shaft, that is of the radius r. That is pi r to the force divided by 2 for solid shaft. Okay, so basically here you can see alpha is the deformation and T is the torque. So by Hooke's law, if you know Hooke's law is say F equal to Kx, right? F is the loading, X is the corresponding deformation. So that means the spring constant equal to F over X. Using this concept, F is the loading, X is the deformation, and we can obtain through this information that is equal to Gj divided by L. This is the equivalent spring constant for a shaft. Right? So if you want to represent the shaft in terms of spring, this is the spring constant. So for the shaft made of the different materials, basically G is different. For different size, they large or small, cross-sectional, then that's going to affect J. Okay, and long or short, they're going to affect L. So everything together, they're going to change in the spring constant. That'll be easier to comprehend. If K is larger, that means it's very stiff, right? If K is very small, then you can easily deform it, right? Okay, so that's about the geometry. And in these sections, and we have the alpha, the angle of the twist being introduced or reviewed. And then we review the beta, that is this definition, and beta will be the symbol being used from today throughout the whole lecture notes, and you will see the beta just appearing again and again. That is by this, okay? And then we move on to define the displacement. So displacement basically, precisely you can see is this. Move from here, this is our U, and move to here, that is our V. UV, for this example, simply in magnitude and direction just like this one. Okay, this will be the starting point. Okay, so now we must move back to here. So maybe in this way we can take a short break.